Thanks for the introduction. Thanks for the invitation. It's a pleasure to be back. So yes, this is the title of the talk. Joint work with Oren Becker and Peter Varju. So I will start with some background on character varieties. So this is we started a finitely presented group. So x1, xk are variable. So generally, it's variables in a free group, and these are words in a free group, and this is a presentation of a group. So it's the free group on K generators with those relations. So that's an arbitrary finitely presented group. And typically, what people are interested in, they take an algebraic group like I would take a semi-simple complex C group. It would help that it's defined over Q sometimes, but you may ignore this for a moment. So, for example, for most of what I'm going to be talking about, if you want, you can just think of SL2C. So it's interesting to look at this set. So this is a set of homomorphisms from gamma to G. It's called the representation variety of gamma to G. And concretely, it's exactly the set of K tuples of elements in G that satisfies those relations. Okay, so clearly it's an affine algebraic set. It's an algebraic variety. Okay. So an algebraic variety, and if your group is defined over Q, then it's also defined over Q, because this is just uses just the group language to find equations. And so this is what's called the representation variety, but it's also clearly conjugation invariant. So it's invariant on the conjugation by G, and therefore it makes sense to mod out by conjugation and to consider what's called the character variety. So we put a double bar here, that's the GIT notation. So this is it's called the character variety. And it's really the affine variety whose coordinate ring is equal to the G invariance of the coordinate ring of the representation variety. Right, so I'll give you maybe a couple of examples. So for example, if you take the free group, if you take gamma to be set free group on two generators, then you take G set to C, and it goes back to Fricke and Klein in the 19th century that this character variety, which the character variety is basically isomorphic to C3, and it has coordinates which are given by the trace of A, the trace of B, and the trace of A. So in this talk, I'm going to be interested in the character variety, but more precisely I'm only going to be looking at an open set in the character variety, which is which I would call X gamma, and that's going to be the open set of tuples that generate a Zariski-dense subgroup in G. Set of Zariski-dense representations. So it's easy fact to check that in a semi-simple algebraic group, the locus the locus of points where the group generated is Zariski-dense. This is an open set. Okay. So X gamma will be an open set, Zariski open set. So everything that's not in X gamma will actually belong to the character variety of a proper algebraic subgroup. So in some sense, it doesn't really live in G, but in a proper subgroup. Okay, so that's what I'm going to be interested in. So in this example, if you do that, then it's going. You need to remove some hypersurface in C3, which is corresponding to the non-Zariski-dense representations. Okay, so so the questions that very natural are following. So for instance, can we compute the dimension? Can we compute the number of irreducible components of this algebraic variety? Can we understand there is the Galois group because it's defined over Q. The Galois group acts on the components, so you can ask for to describe the Galois action on components. And many other interesting questions you can ask about singularities. You can ask about what is the locus of faithful representations. How about discrete representations? Discrete image. So faithful means that there is no kernel.
So sometimes you're talking of the algebraic closeness, sometimes you're talking of some topology as discrete.
Yeah, so here, okay, yeah. I'm not going to be talking about it so much, but this is a question, for example, in SL2C, in GFC. How about integral representations as well? So there is this notion of integral representation of integral type. You may ask when is this the case? Okay, so so for example, another example. If gamma is, let's say, a higher rank lattice, so for instance, SL and Z when n is 3 or more, then we know that in this case, X gamma is finite. And this follows from the Margulis rigidity theorem. SL and Z is just 1 point. So when so typically when X gamma So if you have a representation which is isolated in X gamma, and this is called a rigid representation. So class of form isolated. So the field of rigidity is about trying to understand when a given group has rigid representations, what are the rigid representations of groups and so on. Another example which has been very much studied by a large number of people is the case when gamma is a surface group. And so this has an explicit presentation of the form. Where here, this is the commutator of these two elements. Okay. So, for the surface groups, the answers to those questions are most of the time known. So, for instance, it goes back to a paper of Bary-Soroker. From 1996, that the representation variety of gamma G for the group SLN is irreducible. So it's absolutely irreducible, it's in one piece. And you can also compute its dimension. The dimension is n squared minus 1 times minus 2. So their proof is by hand somehow, uses explicit description of the character variety and using this form, special form of the commutator. It's also very specific to SLN. It's not clear if their approach extends to other groups. And this was here. But this was generalized later on by Liebeck and Schaller. Where they showed the same thing for an arbitrary G. So they show that X gamma G is irreducible and that the dimension is equal to the dimension of G. It's 2T minus 2. So the formula for the dimension is nothing very surprising. It's just basically here you have 2G unknowns, and you have one relation, and then you need to model out by conjugation. So that's why you have 2T minus 2. Okay, but the proof is very different. The proof they use is very different from the previous approach, and it's based on a formula. Well, first of all, it's based on an argument where you reduce mod p and try to count, so counting argument, and then it's based on a formula for Frobenius. It goes back to 100 years ago. So the idea is first of all, well, it's based on the Lang-Bailey estimates. Which asserts that if you have a variety defined of a field then you can estimate the number of points, is the variety over FQ, as the number of components that are defined over Q times Q to the dimension, and this is big O of Q to the dimension 1/2. So in other words, the number of points of the variety, if you can manage to get your hands on the number of points of the variety, then it tells you an information on the dimension, okay, and also on the number of connected components. I mean, at least those that are defined over Q. So that's for the Langevin, but of course you also have this formula for Frobenius that comes into the game. So and Frobenius shows that if you take, that's true for any finite group, so any finite group, then you can compute you can count how many homomorphisms there are from the surface group to the finite group, and the formula is just this. Those formula is the size of H to the 2G minus 1 times the zeta function of H at the point 2G minus 2. So what's the zeta function? So the zeta function is simply the sum over all irreducible characters of 1 over Chi1 to the power S. Okay, so it's a finite sum because it's a finite group. And this formula is explicit. It's actually one of the first applications of character theory that Frobenius invented. So you see that if you combine this with Langevin, then you're going to get what you want as soon as you can prove that the zeta function tends to 1 when t tends to infinity, right? So that's what they show. That's fast. For every s strictly bigger than 1, the zeta function of H tends to 1 as the sine of H tends to infinity, and H is quasi-simple. Quasi-simple group is a group which is simple modulo the center and is perfect. Okay, so that's the case for G of FQ, where G is a algebraic group. So, so this gives you that the count so your group G was a semi-simple Lie group, but it's defined over Q, so you can actually reduce modulo P for large primes and also the powers of primes, and so you get this is you have Q to the 2G minus 1 times 1 and a small error. But G is connected, so there is only one connected component. So this gives, sorry, I'm just erasing what I get here, but that's going to be dimension of G times 2G minus 1 or 1, and you conclude from this that the dimension of the character variety is what you expect it to be. Okay, so that's it for the introduction. So now I'm going to be in this work.
What are they using about surface groups? In this group?
Yeah, so what are they using about surface groups? They're using this. So that's the Frobenius formula, which is only which only works. So it's just character formula. So it only works because we have this particular form of the relator. It's
for another one related group.
Exactly. So if you have another one related group, you have no hope, no chance to get such a formula. This uses crucially the fact that the particular form of this relator, also the fact that the support is disjoint, so it's like you have two G variables and they don't. It's like it has separate supports.
Work for the fundamental group of a surface with orbifold.
Yeah, it does. So actually, it has been generalized. Yeah. So there are formulas was worked by orbits, and so it works for most function groups actually, and indeed Chebotarev worked it out completely. Okay, so right. So if you take another one related group or another word, then this method doesn't seem to be going anywhere. So, however, what we are going to be, so what we do in this work is that we manage to say something in the case when the relators of your presentation are given at random. So random groups.
Just in the sense of grammar.
Yeah, in the sense of Gromov. So let me remind you what that means. So it means that we're going to pick the relators W1, WR independently at random. In the ball or in the sphere, if you want, of radius n, of radius L, so among all words of length L. Okay.
Okay. And what did you said they did it by hand, but can you say a bit more? Or
Yeah. Reduce mod P, they really sort of had a slightly better understanding of the geometry and yeah, so they studied centralizers of elements to look at the dimension of the centralizers and right from there. I mean, it uses SLN in quite a serious way. Maybe it could be generalized, but I think the idea would be much more complicated. Okay, so yeah, so there's work of Kozma and Lubovsky from 2019, where they showed the following fact. They showed that if the number of relators is bigger than log L in this model. So here in this model, we fix the number of generators. If they say that if the number of relators is very large, then in fact, every homomorphism from the random group gamma to GLN and is fixed is either trivial or Z mod 2Z. Either has trivial image, trivial, or Z mod 2Z image. Okay, but here you fix n and you let you, so this holds not for all, but with high probability. here with high probability in this model. Yes.
So you fix the number of number of xi.
Okay. Yeah.
That's k. That's fixed.
K is fixed. The number of generators is fixed, and you let the L tend to infinity. And if you have sufficiently many relators, then your group is sufficiently small, and then it has no. It has no. It doesn't have any interesting image. So, and this is despite the fact that you have a theorem of Galois and Olivier that says that if R is not too big, so let's say less than something like this, then gamma is infinite, and in fact Galois hyperbolic, and you can even combine it with the recent work of Hegel and Wise, which imply that in this situation gamma is linear over Z. So in their situation, there are groups, even though they are linear, they are hyperbolic, they are quite nice, but if you fix the n, they don't have any interesting representations.
About property T, I forget.
Yeah, so property T, it's property T, you can get property T, do you have sufficiently many relations? So that's the at least 1/3.
Linear over Z.
So it just means embedding GL and Z for some n.
Oh.
Yeah. So you can put it in some. There is a certain injective homomorphism to GL and Z. Yeah. For some very large n, it depends on gamma. But if you fix the n, then it doesn't happen. So yeah, so this happens here. The fact that it's not interesting only happens because you have they take too many relators. So in fact, it's interesting that if you take fewer relators, then you get something. You get some interesting algebraic. So let's talk about. So that's the year one. That's our main theorem. So if you, so that it says that there exist constants which depend on K, R, and G, such that the probability at least 1 minus CL, so namely with exponentially an exponentially small proportion of
Wait, what's it? Are we assuming what condition on R in relation to K?
Yeah. I'm about to say. So then if K, if the number of relations exceeds K, then character variety gamma is empty. So here G is fixed. Okay, that's my semi-simple like Lie group. If R is K minus 1, and it's not empty, and it's finite. And on top of this, we can also show that the Galois group acts irreducibly. So it's a single Galois orbit. On the other hand, if you have pure relations, K-2, then X gamma is absolutely irreducible. And its dimension is what you expect. Is equal to, so K minus R minus 1 times dimension G.
Sorry, I cannot read the probability. You say probability 1 minus exponential to the power minus.
Exponential CL. So LL here is
L was what?
L is the length of the relators. So it's the length of the relators. So you pick the relators at random, like this, as words in the free group of length L. Okay, you pick them at random. So you can think of to start with this K equals 2, and you have just one relator. Okay. You pick a word at random of length L, and you wonder what's the character variety you get. Let's say in SL2C.
Okay, thank you very much.
Yeah, and in this case, when R equals 1, K equals 2, we're in the middle case here. And that's the most interesting case because we show that in this case, the character variety is non-empty. So it's really, you do have representations with, and again, X gamma is the part of the representation variety, which is Zariski dense. So we get Zariski dense representations. We do get groups. So subgroups of SL2C that are two generated subgroups, and we know they are Zariski dense, and they satisfy this relation.
I assume it's quite robust in terms of how you choose a random element.
It's quite robust, yes. So that's right. Yeah. So we can either choose it uniformly on the sphere or on the ball. We can also take random walks. Yeah.
Okay. The things you get in part 2, do they tend to live inside a maximal compact?
No, so typically no, but they may. So the Galois group will act on them.
Yeah.
So sometimes you will end up in SU2 and or maximal compact, or sometimes not. So it really depends. So it's a bit like asking if you take a random polynomial, am I going to get a root on the unit circle?
Right.
Yeah, sometimes yes, sometimes not. So that's, there are many interesting questions that can be asked. For example, you can ask, can you find among this finite set of representations, can you find one that actually lives in SL2R, in the real part? That's if you compare with random polynomial models, then you would expect typically to have something like a proportion of log L of them to have. So you
Well, that's very sensitive to what your model is. That's why I asked you that.
Yeah.
If you take a random polynomial, let's say real coefficient.
Yeah. So what's the this is a kind of a non-abelian version of a random polynomial model where you take the degree to go to infinity and the coefficients to stay bounded. It's kind of the idea. So here, when you do this, so you can see this analogy in the case of SL2 by looking at the trace. So it's well known that the trace of W of AB is in fact some polynomial in the trace of A, trace of B, trace of AB. And this polynomial has integer coefficients. And if your word has length L, the polynomial will have degree L. But the coefficients won't be bounded, they will be exponentially growing. But and the set of polynomials that you get is still a very thin set in the family of polynomials of degree L. The coefficients, let's say 2 to the L. But this is what we are looking at. So one thing I should say is that this is not a theorem because it's on GRH.
Let me add that it's not fair. No, I'm kidding.
Okay. So it's under GRH, so we don't need the full force of GRH, but we need no Ziegel zeros for Dedekind and Zeta functions for fields that come up.
So it's similar to your other work with Varju, where you have to assume GRH, and it's not obvious how to get rid of it.
That's right.
You need GRH to get the exponential error term or to get anything.
Anything. Yeah. So yeah. So about the exponential error term, the fact that you have an exponential error term here tells you something interesting.
By the way, when R equals K minus 2,
Yeah.
the first time it's positive dimensional, I think.
Yeah.
Do you know any algebraic properties of the variety, like in the surface group? These things don't tend to be the F log Calabi-Yau. Do you know anything like that?
Yeah, no, we don't. I mean, I would expect it to be smooth most of the time.
I'm more interested in whether it's kind of, what its topology is. Because those turn out to be rather interesting. And of course, the integer points on those are more interesting.
Cool. Yeah, no. So I don't know about the topology of it, whether it's rational or I don't know. Yeah. So it's a consequence here of one is that this equation for all pairs A and B that generated the dense subgroup of the probability when you take a random word of length L, and this random word vanishes. These are G. Well, this decay is exponentially fast. And the C here does not depend on A and B. And so this has a name, it's called uniform non-immutability. And this is something that I knew before, and it's because it's a consequence of the uniform Tietze alternative. But it's just show you that such a statement actually is of this strength. Okay, so now I'll talk about the method a little bit. So why is that? It's because if this was not true, then you could pick 2 at random, and you would still get exponentially many. So actually here with the same C as before, it's C over 2, and therefore you would get non-emptiness in case 1. Okay, so a few words about the method. Well, okay, so there's no Frobenius formula for arbitrary words. Okay. But nevertheless, we can still apply.
In fact, I still understand Gromov in connection with this.
Yeah.
One of the hard things with Gromov is that you don't get the trivial group. What's his range? Or what?
Yeah, I just erased it. But so in his range, you don't get the trivial group as soon as R is less than 2k minus 1 or
Square root.
Yeah, square root. And you get property T if it's bigger than 1/3.
Okay, so it's quite subtle.
Sufficiently many.
And you have the K, okay.
I fix K. So people who do random groups, they call it we call the model we work with the few relator model. You fix the number of relators. And for a good reason, because as soon as you take sufficiently many, then it's not interesting. You don't get representation.
One is strictly stronger than this. So you're saying that uniform case alternative is a consequence of
No,
one?
so the uniform non-amenability
yes,
is a consequence, but yeah. Okay, so the method, all right, so we call the Langevin estimates, but in relation to this, there is also the Chebotarev theorem. But this is the key behind this method. So the Chebotarev theorem, identity theorem, can be formulated also for varieties. And there is a beautiful book by Serre called NXP that explains it all. NXP is the number of points in the variety over FP. And in particular, you have these two facts. So the first thing is, if you have a variety Y, C over Q, then you can tell its dimension by looking at the lim sup of the number of points as over FP. And more precisely, if you average the number of points in window, say a moving window of primes. So here I take the expectation, so that's the average number of primes, average over the number of primes of the size of y of p divided by p to the dimension. Then this becomes, do you know what this becomes? Becomes the number of irreducible components over Q. Okay. So that's the number of Q irreducible components. The reason for this is essentially that, so one way to think about it is that for the
is that Q or Q bar?
Q, really over Q.
Okay.
So,
One over this, it's log P, right? And
yeah, thank you.
and it's only for irreducible or for any?
Yeah, you don't need, yeah. Okay, so the idea of this is that the idea of Chebotarev is that the Frobenius of prime P in the Galois group, it redistributes in the Galois group. And so, in particular, when you write something like this, then by Langevin, this is Langevin. This is roughly the number of components of Y that I define over FP. So this is essentially the number of fixed points of Frobenius where you see the Galois group acting on the set of irreducible components of Y. Okay. So the Galois group acts on the irreducible components, permutes them. And how many are defined over FP? Well, exactly the number of fixed points with Frobenius. But then you have a basic lemma in group theory, which some group theorists call the lemma that's not Burnside's, because it appears in Burnside's book, It was called Bernstein's lemma for a long time. Then people discovered that it was due to Cauchy or something. And it's the fact that if you have a group, finite group acting on a balanced set, then the average number of fixed points, the number of fixed points of H is equal to the number of orbits. Okay. So when you think about it this way, then you see that what Chebotarev tells you is that Frobenius will equidistribute in the Galois group. And therefore, when you average over the primes, you get exactly the distribution of a random element of the Galois group. And when you average the number of fixed points of a random element of the Galois group, you get the number of orbits. So you get the number of Galois orbits acting on the components, and that's exactly the number of two irreducible components. Okay, so that's the idea. And okay, so as I said, even though we cannot access, we don't have a Frobenius formula, so we cannot access directly the number of points of my let me call it y gamma, where y gamma is the representation variety of my random group gamma in G. Okay, we don't have a formula for this because the words involving the definition of the presentation are complicated. We don't have a formula for it, but so we don't have direct knowledge of this. But what we can do is we can average over the random group, and this leads some information. Okay, so we can average, and when you write the average, so here now I average over gamma, okay, of the number of points, so the number of homomorphisms from gamma to G of P. So if I just write this, just compute, then this is going to be the sum of over all tuples G of P to the K, and I'm only going to be looking at the tuples that generate, because I'm only looking at the part of the character variety that's Zariski dense. And here I have the expectation of the gamma of what? Of those tuples that actually belong to the variety. So that's indicator function of W1. That's indicator function of WR. So this is therefore just the sum, again, over the star of basically, because they are independent, choose them independently, these relators, it's going to be the probability when I choose a word of length L that W of X bar equals 1 in G of P. Okay. And now I can understand this because I know so much about random walks on groups. So so this brings me to so if I know that this is essentially that the random walk is equidistributed in the random walk in the group, then I will know that this is. So I forgot the power R here, all of them. Right. Then I will know that this is sum over X of 1 over G of P to the power R, and therefore G of P to the power K minus L in total. But of course, I need to justify these signs here. And for this, you need uniform exponential mixing of random walks on G of P. So what do I mean by this? I mean that I need an estimate that is uniform in the generating set. So something like this. It's maybe less than, let's say, G of P to the 10 or something, to the 100. I need this to hold as soon as L is bigger, let's say, than some constant times log P. And for those of you that were here in 2005, 2006, you know that this is exactly what it means to be an expander. And so this takes us to the next result, which is M2. It's a generalization of work I did here with Alex, and it says following. So for every finite, there exists some family of primes.
By the way, so in the way with Varju on the irreducibility with the 0-1 polynomials, it was abelian.
Yeah,
There's nothing abelian, yeah? Is that correct?
that's right.
So it's easier in some sense that you know, but there you needed the Riemann hypothesis for small split prime, probably. I can't remember. Now it was Chebotarev, uniform Chebotarev. So where's it coming in here?
It's coming in. It's coming in the same place into effective Chebotarev. So, yeah. Sorry, so it's coming in when you do this here, when you try to affect this not boundary lemma to say that they are the same. You can only say so if.
Yeah. Okay, so it's a
Chebotarev,
but it's not what you needed in that other paper.
It's the same. It's related, very related.
Okay.
Yeah.
But the other one was an abelian.
But still, the Galois group is not abelian.
Yeah.
But you're right that the random walk stuff
Was on just on
was on a fine group.
Yeah.
The difference, yeah, it was on a fine group. Here it's on simple group.
Yeah.
That's yeah. Okay, so I just finished stating this theorem. So there's a set of primes, maybe small, but maybe infinite, such that the set of it's quite small in that sense. So there are very few primes. And the second point is that for every P, which is not in this possibly small exponential, possibly small exceptional set, the family of all Cayley graphs, so all Cayley graphs, of G of P is an expander family. Okay. And this is absolutely needed to be able to affect this argument that I sketched on the board, because you sum over all. Here you sum over all points, and if by some you know if you were unlucky and an X bar would lead to a non-expander with an X bar which was not which would not equidistribute fast, then this would completely ruin this estimate. So you need something like this, and so this generalizes work of Alex, Gambrot, and myself from 2010 or something like that. where we did the case of SL2. Okay, sorry. Good stuff.
Further questions?
So am I right that your argument gives a little more in the following sense, that if the number of relations is less than or equal to k minus 1, and you think about them as giving a morphism from g to the k to g to the r, then the words is giving a morphism, and this morphism with probability approaching 1 will be faithfully flat.
Yeah, that could be, yes. Actually, I'm aware of your question in your paper. It may very well be the case, actually. Maybe we could talk about it. Yeah.
You have any opportunity to make use of port gamma acting on this? Outward gamma.
Yeah, out of gamma. Yeah.
Not yet.
That would be very interesting.
Can you say anything meaningful about the dependence of this constant on the Lie group G?
It's effective, but it's kind of complicated.
How does it grow?
It grows with the dimension pretty badly. And how does it grow with K and R? I don't know, but will also pretty badly. Everything, because everything there, to make all the estimates work, you need to write down the estimates, and you deal with varieties that are defined over number fields whose degree grow, and the varieties live in finite dimension. They're finite dimensional, but again, all the estimates depend on the dimension, so everything blows up and the dimension grows.
I have one technical question. In your work with Alex, last thing, you needed K3 or 4, not K2. Because of, so I'm just wondering, you don't have any condition on K in general. K could be 2.
Could be 2.
So you don't face this Weigel, pairs of generators being able to move around. That would be exactly my other question, where you work with Ort. That doesn't come up at all.
Yeah, no, it doesn't come up because it's okay if they don't belong to the same orbit of the outer automorphism group, then it's okay.
So we distributed already, yeah.
Okay. If there are no further questions, then let's thank the speaker.